Okay. Do you know what it is, or do I need to bust out my book?
We can do one from this one.
Okay, I'll ask that.
Because I don't know what it is.
Okay, I think, is that the one where you got a rectangle underneath a curve or something?
No, it was the cylinder one.
Or the cylinder one?
But we can do a different one. Can we do number 4 on this ground?
4 on this ground. Can you tell me what that is?
A container in the shape of a right circular cylinder with no top has a surface area of 3 pi feet squared.
Is it about 3 pi?
Yeah.
I'm just going to call it area instead of surface area.
What height and radius will maximize the volume of the cylinder?
What, the maximum volume?
Yeah.
Okay. And we know volume of a cylinder is pi r squared h. Okay, and the area, did this cylinder have a top or no? Do you know?
No top.
Okay. So there's 2 circles for the top and bottom. So if you had both the top and bottom, it'd be 2 pi r squared. But if there's no top, then it's just a pi r squared. And that rolled up part, curiously enough, you know, it seems mysterious, but if you take a cylinder and you slice it and then you unravel it, it's really just a rectangle, which we know is base times height, where you got the base, or we usually call it the height of the cylinder, and then the other part is just the circumference of that circle. So it's 2 pi r h. So there's the circumference, which is one side of that rectangle, and then the height of the actual cylinder. So we got the h is this distance, and we got the radius is this distance. Okay, so this is what we want to maximize, and always an optimization problem is going to be looking for an absolute maximum or an absolute minimum. So it's always going to require a justification, even if it doesn't say that. So you're going to have to justify why it is the maximum or the minimum. So here we have, now if we try to do our calculus on this, the problem is we've got 2 variables and then it gets to be a big mess. So we want to use what we know about the area to replace one of these variables and make it into a function of only one variable. Then we can use our calculus to take the derivative and look for critical points. So I think it's really a mess to try to solve for r there. Not that it's going to be pretty to solve for h, but relatively speaking, solving this for h is going to be, and then substituting it in here, is going to be far easier than trying to solve for r, because you've got the r's in different places, and one is squared and one isn't. So we know the area is 3 pi, so we can plug that in right there. Now we're going to solve it for h, so that we can get rid of the variable h in the thing we're trying to maximize. Does that make sense? Why we're doing what we are? Okay. So I'm going to subtract the pi r squared, and then we'll divide through by 2 pi r. So, and I think it might be easier to do them separate so we can get whatever cancellation out of this we can. So I'm going to put them into 2 terms instead of one big fraction. So then we can cancel the pi's, and I'm going to maybe write that as 3 halves and then call that r to the -1. You don't have to do that. And then here, the pi's cancel and one of the r's cancels. So I'm going to write that as a -1/2 r for RH, or our h. Is that okay?
Is that an r?
Clearly that's an r. Something better. So now we're going to plug this in for this h into the thing we're trying to maximize. So that's going to become volume is pi r squared times 3 halves r to the negative 1 minus 1 half r. And we can distribute that. And so this is going to be, I'm going to combine these, the 3 halves and the pi, and just lump them together as 3 pi over 2. That's just a constant. And then the r squared times r to the negative 1 is just r. And let's see, that's going to be, I'm going to call it a pi over 2 just to kind of condense the constant part. And then r squared times r is going to be r to the third. Is that okay? Okay, now here we go. We're going to take the derivative of the volume here with respect to r. So you call it v prime or dv dr, whichever you want. And so the r is the independent variable. So that's going to be 3 pi over 2 minus, and bring the 3 in front, so that's another 3 pi over 2 r squared. We're looking for critical points, so there's nothing that'll make this undefined. We don't have any r's in the denominator, but we want to know what's going to make that equal to 0. So I'm just going to add this to the other side to get 3 pi over 2 is 3 pi over 2 r squared. We divide out the 3 pi over 2's, and in this pretty carefully constructed problem, r squared is 1. Now we should probably think about what the domain is, because at some point in time we're going to have to argue that this is an absolute maximum, and it's going to depend on the domain. I don't think really anything can limit that, except that I don't think it would make sense to have a negative or probably even a 0 for r. So our domain, I think the best we can do is say that r has to be greater than 0. So then when we take the square root of both sides, we reject the negative 1. So it's true that negative 1 is a solution to r squared equals 1, but that's not really feasible for us. So it's a good news thing that we have only one critical point. That's going to make our life easier as we try to argue why this is going to be an absolute maximum. Because we have a domain that is not a closed interval. When we have a closed interval domain, we can use what's called that candidate test. So if this has a maximum or a minimum, it's going to occur either at a critical point or at an endpoint. So if we had endpoints, like say it was 0 to 5, we could plug in 0, plug in 5, plug in the critical point. Or if we had a list of critical points, all of the critical points, whatever gave us the largest value is the maximum. Whatever gives us the smallest value is the minimum. That's the cleanest, easiest way to do it. Because this is not a closed interval domain, it gets a little harder to argue. So that's what we're looking at now. So if we look at our domain, we're going from 0 to forever, and our only critical point is 1. So if we check a value in between 0 and 1, like say a half, and we plug that into our derivative, we want to know is the derivative positive or negative. So 1/2 squared is 1/4, times this is going to be 3/8, so that's smaller than the 3 halves, which means this is going to be positive. You with me? I pick something bigger, like say, I don't know, 100. You know, as this gets bigger, then this is bigger than this, and so the difference is going to be negative. So it is changing from positive to negative. Okay, now, as it is right now, we can argue that this is a relative maximum. It's a relative maximum because the derivative changes from positive to negative. Then we can argue that. So we're going to say that, okay? I'm going to say that V has a relative max at r equals 1 because V prime changes from positive to negative, period. Now, because it's the only critical point on the domain, that makes it an absolute maximum. because it's increasing everywhere to the left and then decreasing everywhere to the right, that's going to make that the highest mountain in the range. Okay, so the has, or I could even say the of 1 is the maximum. That's the absolute maximum, because r equals 1 is the only critical point. So that's how we can go from a relative maximum to an absolute maximum. If there's more than one critical point, it gets significantly more difficult, because then this argument doesn't hold any longer. Okay? Does that help, Miranda, at all? It's tough stuff. There's no way around it. It's tough stuff. Okay. Any short questions, or can I kind of have to start talking about related rates here. And then if I can squeeze in some time at the end, that would be a little doubtful, actually. We can try. Okay. I did do a video on these. Did you see that? That it goes through and explains those problems on Miss Brown? Okay. That was still confusing?
No, I was just struggling with the derivative.
Okay. Did that help? Seeing it? Okay. Good. Good. Okay. So what I want to talk then about here is related rates. So I used to think, I thought related rates was the hardest thing, but over the years, students have argued vehemently that optimization is harder than related rates. So I stand corrected. But it's challenging. So this is a new and different idea. So this is 4.6. I'm going to talk about related rates. So here's an idea. We know that the area of a circle is pi r squared. And so the way that is written, area is a function of the radius. So you choose what the radius is, that determines what the area of that circle is. So we could, if we wanted, call this, I mean, it might be a little pretentious, but we could say it's area is a function of r. A of r is pi r squared. And we could take the derivative and say that the derivative of a with respect to r would be 2 pi r. Now, suppose radius is a function of time. It changes with time. If it changes with time, then that in turn forces area to in fact be a function of time as well. So here's a scenario to kind of imagine how that might happen. So imagine there's a really calm pool and you drop a pebble in there and you see a ripple go out from that very calm water. So if you just watch one of those ripples, that's a circle and its radius is changing with time. So as that radius changes with time, so too does the area change with time. So it becomes then, the situation changes from just this simple area is a function of radius to area is a function of time, because the radius is a function of time. And so then when you go to differentiate this, we're not differentiating with respect to r, because r is no longer the independent variable. Now we're differentiating with respect to t. And so we are, when we take the derivative with respect to t, this becomes a dA dt, the derivative of the area with respect to t. And now this, the r of t squared, becomes a chain rule derivative because it's a function raised to a power. So it's going to become 2 pi r of t to the first. Now we would have, like when we do implicit differentiation, we would just call it y prime or r prime. But now what's usually done is you try to emphasize the fact that the new variable is t, and so it's usually written as dr dt. So you get related rates. You have two rates of change that are related to each other in this same equation. So two different rates of change in one equation, and that's where the name related rates comes from. So what makes it more confusing, I think, or what adds to the confusion is that people don't write it this way. You'll have to get from context. It'll still be given to you as, you know, a equals pi r squared, but from some context in the problem, you'll understand that the radius is changing with time. And so then the way that will usually be written is we'll say dA dt is going to be 2 pi r dr dt. But it's from clues given in the problem rather than the way that it's written that tells you that everything is, that we have these different functions of time. And so that, I think, makes it even like it's disguised or something. Okay? Okay. Then once you get to here, you'll be given enough information in the context of the problem usually, where you're going to know everything but one thing. So you might know the dA dt and the radius, and you're going to solve for the dr dt. Or you might know the dr dt and the radius, and you're going to solve for the dA dt. And so part of that information will be given as rates of change. And so you have to read carefully as a calculus student to pick up on what's a derivative and what's not. Okay? And that you don't plug in, you may be given, you know, we're interested in what's the rate of change of the area when the radius is 5, but we're not going to plug the 5 in immediately because it's going to be changing with time until we differentiate it and then plug it in. So there's some interpretation that goes with that too. Let me give you a couple examples, and then I've got a notes sheet for you as well that we'll try to start on at least a little bit. So if we have, let me make sure I say it the way I want to say it. Pretty good catch. Suppose a cylinder has radius 5. Suppose a cylinder has radius 5, but the height h changes with time. And so then I'll say, therefore, the volume also changes with time. And we know that the volume formula for a cylinder is pi r squared h. You don't have to memorize those. So let's see what we get when we then, how would we take the derivative here? And the big point is, when do we substitute in the 5 for the r? So since the 5 is not changing with time, we don't have to treat it as a function of time here, and we're free to substitute the 5 in before we differentiate. If the radius was changing with time, and we were trying to find something else, maybe dV dt, the rate of change of the volume or the rate of change of the height, when the height was 5, we would have to differentiate first and then plug in the 5. So you have to make sure you understand, does this variable change with time or not? If it does change with time, you have to do the derivative before you substitute in numbers for it. In this case, it's constant, so we're okay to plug that in first before we differentiate. Does that make sense? And that's something you have to read carefully for. So now we differentiate this, we're going to get, what do you V prime? You know, we won't, but it's V prime, but we're going to call it dV dt to emphasize the fact that the time is the independent variable. And then what will we get here? 25 pi dH dt. So remember, that is a function of time, so it's not just one. Okay? Okay, now compare and contrast that with, suppose we have a cone and both the radius and the height change with time. Suppose say, and therefore the volume change with time. So the formula for the volume of a cone is 1/3 pi r squared h. So in this scenario, both the radius and the height are changing with time. Therefore, the volume is going to change with time as well. So now, if we go to take a derivative of this with respect to t, what rule are we going to have to follow on the right side here? And it's going to become a product rule, which is going to make this way more complicated. Does that make sense? Because we don't have anything that we can plug in there. Both the r and the h are functions of time. So then we get dv dt, and however you want to do this, the 1/3 pi, if you want to hold it out and then do your product rule, then we're going to get the first, r squared, times the derivative of the second, which is going to be dh dt, right? So that's some unknown function of time, plus the second h times the derivative of the r squared, which is now going to be a chain rule derivative. So that's going to be, so I'm going to go 2r times dr dt. And so you can see now there ends up being 3 of these rates of change. There's a dv dt, a dh dt, and a dr dt. There's 3 of those. So we would need lots of information in order to be able to solve something here. Okay, so I have a note sheet for you. It's on Canvas. We can work on that together here. There it is. So you can go ahead and take a look at that first one. I think we have talked about that enough that you have a fighting chance on that. So see if you can read through that and try to do that, and you can certainly talk about it. So we have the volume of a sphere is 4/3 pi r cubed. What'd you get?
dv dt equals 4 pi r squared dr dt.
Nice. See how we're getting there? So using our chain rule, the 3 comes down, cancels with the 3 and the 4/3. We get r to the second, and then times the derivative of r, which is dr dt. Anybody here like a formula guru? Do you know what this is the volume formula of a sphere? Do you know what the 4 pi r squared is a formula of? It's the surface area. So in a sense, what you're seeing, that if you have this, if you have this sphere and it's changing, the volume is changing, either it's, you've got like say a snowball, and it's melting a little bit, so its volume changes a little bit. You're going to kind of peel off one layer of that surface area, and the volume changes by just that little slice. Or, if it's freezing and it's growing, it's going to gain just like one layer of surface area kind of thing. Kind of interesting to see. Okay, take a look at the second one. We did this one, so see if you can do it here. Gavin?
Let's see, I got r squared times dh over dt, and then plus h, it would be times 2r dr dt.
Very nice. We in agreement? Okay. So, now the gloves are off and it gets serious. Okay, so let's read the next one and see if we can sort this through. So when you read these two, it's like you have to be like a detective. So like Sherlock Holmes, you're looking for clues here. So when you read this, you just got to jot down every little piece of information that you can get out of that. So I'm going to read it with you here, but I'll try to highlight some things that are really important. So a hot air balloon rising straight up from a level field, so it's rising, it's going to be changing, something's changing here, is tracked by a rangefinder 500 feet from the liftoff point. So we've got this balloon, and it's 500 feet away from something over here, some kind of instrument, a rangefinder. At the moment, the rangefinder's elevation angle is pi over 4. So this thing that's measuring the angle, I'm going to call it, say, theta. So we know that as that balloon rises, that angle theta is changing with time. So it's a function of time, right? And so we know that the moment in time we're interested in is when it's pi over 4, but we know that theta is actually a function of time. It's changing with time. The angle is increasing at a rate of 14 radians per minute. So what is that telling us if the angle is increasing at 14 radians per minute? In the language of calculus, what is that telling us?
The height is a function of time.
Height is a function of time also. Yep, so that's going to be in there. That's a function of time. The angle theta is a function of time.
At the point pi over 4, the derivative is 0.14.
So the derivative of what? You're right. The derivative of what?
Sine of, what did we, sine of,
It's just the angle itself.
okay, I got you.
So that's because it's radians per minute. So that's a measurement of an angle. So it's the theta dt is 0.14. Kind of crazy, huh? Does that make sense? And so the units can be clues too to what that's given us. So when you see a rate, it's like a bell has to go off. You're like, that's a derivative. So a rate of change is a derivative. Derivative of what? Well, sometimes the units can clarify what that is. Since it's radians per minute, that's a measurement of an angle per time. So that's a d theta dt. And we're looking for how fast is the balloon rising. So what is that? What is it that we're looking for?
Height.
It's a rate of change of the height. So it's a derivative. We're looking for the h dt. And I think that helps to write that down too, so we know what it is we're looking for. So these are all the pieces that we know. So now we need something that connects them all. You got a theta, you got 500, you got h. What connects all those together?
Cosine of, no, it'd be tangent.
Via tangent.
Yeah.
Okay, because you have opposite and adjacent. So you have a tangent of theta is going to be h over 500. Now remember the tangent, that the theta and the h are both functions of time. So should we go ahead and differentiate that? Now here's the question that people get into trouble with. Can we plug the pi over 4 in for theta first, or do we have to differentiate first and then plug in the pi over 4?
Differentiate first.
And why? That's correct. And how did you know that you have to differentiate first?
I sure you say it before. I
Because
don't
it
know.
changes with time.
Because theta is changing with time. So that is, we want to, if we plug in the constant, we take away its ability to change with time. If it's a constant, its derivative is going to be 0, it's gone. But it is changing with time, so we have to differentiate first and then plug in what we know for the theta. So you have to give that careful consideration. So we're going to differentiate everything here with respect to t. So now I have tangent of theta is a chain rule derivative. So the derivative of tangent is secant squared theta times the derivative of the inside function. Exactly, we're going to call that d theta dt. You with me? See how we did that?
Right, how do we do that?
So this is a function theta of t inside the tangent.
Oh, yeah.
So it's a chain rule. There's a derivative of the outside function, leave the inside function alone, times that derivative of the inside function, and we're going to call that d theta dt. On the other side, do we have to use the quotient rule? No. Yeah, it's 1 over 500 times h, so its derivative is going to be 1 over 500 times dh dt. Very nice. So good so far? Okay, now we're going to evaluate secant squared theta. Well, now is where, so this is changing. Theta is changing with time. So this is a dynamic situation here, and then we're going to freeze it right at the moment where that angle is at pi over 4. And then when it's frozen there, we're going to try to figure out, well, how fast was it rising right at that moment in time. So it's like one frame in this movie. Okay. So we're going to plug in pi over 4. So secant is 1 over cosine. So we want the cosine of pi over 4 squared. That's going to be a 0.14. And we're going to try to solve for the dh dt here. So let's see. Cosine of pi over 4, what's that? Good. And if we square that, what does that become? 2 over 4, which is otherwise known as, and to divide by a half is to multiply by, so it's going to become 2. So this whole secant squared of pi over 4 is 2. So that's going to be 2 times the, what did we say that was? I don't think I said that right. Was it negative? I don't think so. I don't know why I said negative. It was 0.14, wasn't it?
Yeah.
So that's going to be a 0.28. Is that right? Oh, I'm going to save it. Hold on. I'm going to leave it as 2 for a moment because I'm going to bring that 500 over in a second. Is that okay? So we're going to have to multiply by 500. The 500 times 2 makes 1,000. Then 1,000 times 0.14, you're just going to move that decimal over 3 places. So our dh dt is going to be 140? Yeah, good. I was just going to ask that. What is the units? That's going to be feet per minute. Is that making sense? All right. Well, with our confidence boosted, we'll turn that page over and do a car chase in 4 minutes or less. So let's give some variables that we're going to put in here in this police chase here. It kind of looks like an XY axis. So let's say this speeding car, its distance is going to be X. And the police cruiser, its distance from the intersection is going to be Y. Does that make sense? So the X is the distance the speeding car is from that intersection going east. And the Y is the distance the police cruiser is from the intersection, and it's going south. It's north of the intersection, but it's moving south. So let's see, when the cruiser is 0.6 miles north, what's that telling us? Y is equal to 0.6. Then the car is 0.8 miles east. And the distance between the cruiser and the car is increasing at 20. Increasing at 20. What in the world? So we need a distance between those. Okay, what do you want to call that? D? I'm good with that. So the distance is the distance between them and the car is increasing. So this is weird notation, but that's a dd dt is 20. That makes sense? So the change in that distance between them is 20. Now here's where you have to be a little careful. The cruiser is moving at 60 miles per hour. What is that telling us? What is it?
Is that a point?
It's not a point. It's miles per hour.
Oh.
It's the y is a function of time.
Well, it's not the y. It's not the y function. If it's miles per hour is a rate of change.
Would it be dp over dt?
Well, but we've called this y.
Oh, so dy.
dy dt. Okay, now be careful because that's the speed. But as you look at that picture, is that y value getting bigger or getting smaller? So that dy dt is going to be, a velocity needs a sign. Is it positive or is it negative? See how it's going to be a negative? 60. And what is it we're looking for? Very good. Yes. You want the speed of the car, and that's going to be what's the velocity of that x? The rate of change of the x. Does that make sense? So what's the relationship between x and y and d? So you're going to get x squared plus y squared equals d squared. Okay. Now we got more to do. See what you can do. We can talk more. There's a video on this that works through this. But trying to do them, especially with somebody, I think is helpful. These are really tough to do all by yourself. So these would lend themselves well to collaboration.